On that day, 3I Atlas, the interstellar visitor racing through our solar system, will pass within 33.21 million miles of Jupiter. You might think that's just another close approach. A random flyby. Space is big, things pass near planets. Except that distance isn't random. It's almost exactly Jupiter's Hill radius, the invisible gravitational boundary where Jupiter's pull becomes stronger than the Sun's. The difference between 3I Atlas's path and that boundary? Just 35,000 miles. Out of 33 million, that's a hit on the target to within 1/10%. The statistical probability of a natural object randomly passing this close to such a gravitational threshold, roughly 0.004%. Around 1 chance in 26,000. If this was just a comet, we wouldn't be dissecting it together. But it wasn't. Subscribe and leave a comment with your theory before we uncover the next part. Because what happened to put 3I Atlas on this path isn't luck, it's physics. Astronomers monitoring 3I Atlas earlier in its journey noticed something strange. The object's trajectory was deviating slightly from the path predicted purely by gravitational interactions with the Sun and planets. These deviations were subtle, but measurable. An acceleration of approximately 5x10⁷ astronomical units per day squared. That might sound obscure, but it means some force other than gravity was acting on the object, altering its motion by a measurable amount. Natural comets experience this all the time. As they approach the Sun, volatile materials warm up and sublimate, producing jets of gas and dust. These jets act like natural thrusters, giving small pushes that shift the trajectory. But natural outgassing is chaotic. The location of volatile pockets, the orientation of rotation, the distribution of sunlight, all these variables create messy, unpredictable jet activity. For outgassing to push a comet by exactly the amount needed to redirect it by 62,000 miles, the difference between its original path and its current trajectory near Jupiter's Hill boundary would require precision that's extremely unusual for a naturally active body. Yet the acceleration measured in 3I Atlas produced exactly that trajectory shift. The object's path was altered just enough to guide it from where it would have been, heading naturally to a course aligned with the invisible threshold around Jupiter. Even if you assume a highly active comet with strong jets hitting a gravitational boundary to within a few tens of thousands of miles across millions of miles of travel remains an extraordinary coincidence. Jupiter's Hill radius isn't just a theoretical line. It's a calculated value derived from exact physical parameters. The mass of Jupiter, the mass of the Sun, the precise positions and velocities of both objects. For March the 16th, 2026, the calculated Hill radius for Jupiter is approximately 33.24 million miles. 3I Atlas will pass at 33.21 million miles. Inside this boundary, Jupiter's gravity can seize objects, draw them into long-term orbits, or significantly redirect their motion. Outside, the Sun's influence is overpowering, and sitting along this boundary are the Lagrange points, regions where the gravitational pull of Jupiter and the Sun balance in such a way that an object can remain stable with minimal energy expenditure. More than 230 observatories across the globe have been tracking 3I Atlas. Data has been flooding into NASA's Jet Propulsion Laboratory, forming a comprehensive observational network. These measurements allowed scientists to calculate the object's expected distance from Jupiter with extraordinary precision, and the numbers are unmistakable. The object didn't drift into this trajectory. It was pushed there by forces measured and documented, forces that aligned perfectly with what would be needed to reach Jupiter's gravitational boundary. Harvard physicist Avi Loeb points out that the statistical improbability, combined with the measured acceleration, warrants consideration of all possibilities, including the presence of a propulsion mechanism or other engineered feature. In Loeb's interpretation, the object may have made deliberate micro-adjustments, steering itself toward a region of gravitational stability around Jupiter for reasons unknown. However, the lack of direct evidence for artificial origin remains a major obstacle. No radio signals have been detected, no thermal signatures indicating waste heat from an engine, no visible structures or emissions. To date, the only anomalies are the trajectory, the acceleration, and the statistical unlikelihood of the configuration. As scientists often note, extraordinary claims require extraordinary evidence, and none has emerged yet that would definitively support a technological explanation. Other possibilities are being explored with equal rigor. One is that the calculations regarding the object's orbit may still contain slight inaccuracies. Even with hundreds of observatories contributing data, small uncertainties remain. A tiny unaccounted gravitational influence could theoretically shift the predicted path. If the initial trajectory estimates are off by tens of thousands of miles, then the observed alignment with the hill radius could be an illusion created by incomplete modeling. Another explanation involves exotic comet physics. Interstellar comets may contain volatile materials or structural characteristics never before observed in solar system comets. If 3I Atlas possesses an unusually uniform distribution of volatile materials, or an internal structure that channels sublimating gases in a stable direction, then its non-gravitational acceleration could be far more consistent than typically observed. This would allow outgassing to act in a controlled manner, inadvertently producing a trajectory shift that happens to intersect precisely with Jupiter's hill radius. A third explanation, embraced by the majority of astronomers, is simple coincidence. Over billions of years, countless interstellar objects have passed through the solar system. In such enormous time spans, statistically improbable events can and do occur. The fact that 3I Atlas is only the third interstellar object detected doesn't necessarily reflect reality, only the limits of current detection methods. If millions of similar objects have passed unnoticed, then one random alignment with Jupiter's hill radius isn't unreasonable. Even so, the coincidence explanation leaves open important scientific questions. If the trajectory is random, why is the non-gravitational acceleration so precisely aligned with the required shift? Why did the object's path deviate in exactly the direction needed to close the gap? And why, among the few objects finally detected, is such a statistically rare event occurring now with one of the earliest interstellar visitors that modern astronomy has been able to study in detail? These questions drive continued interest in the object and the upcoming close encounter with Jupiter. As the approach draws nearer, observatories are preparing for a flood of new information. Additional observations will soon refine the object's path to an even greater degree of precision. Data gathered during the March encounter will be pivotal. Gravitational interactions with Jupiter will either confirm the object's expected path or produce new deviations that shed light on the underlying processes steering it. Over the next several months, astronomers anticipate that increasingly detailed measurements will help determine whether 3I Atlas is a natural comet behaving in an unexpected way, the product of an error in orbital estimation, a statistical rarity, or something more complex. No matter the outcome, the object's trajectory has already sparked one of the most intriguing scientific puzzles of recent years. Its arrival at Jupiter's boundary carries with it the potential to deepen understanding of interstellar visitors and challenge assumptions about the quiet regions between stars. The scientific world now waits for the moment of closest approach when data and physics will reveal whether 3I Atlas is an improbable outlier, an exemplar of unknown cometary behavior, or the first sign of something that defies the familiar patterns of the solar system. Because if this alignment isn't coincidence, if those micro-adjustments were deliberate, if something guided this object across light years to arrive at this exact location at this exact time, then March 16, 2026 isn't just another date. It's first contact.